Thank you for tuning into this webcast. I'm John Klein from the Carnegie Mellon University Software Engineering Institute. My colleagues and I have been working on architecture analysis early in the life cycle, and this presentation will introduce you to our work. Software Engineering Institute is a federally funded R&D center sponsored by the Undersecretary of Defense for Research and Engineering. Now, software architectures are not inherently good or bad. What's right for one system is not necessarily right for another. Good architecture is one that's fit for purpose, that allows the system to meet its functional, quality attribute, and lifecycle requirements. But we can divide these requirements into two broad categories. The first is requirements like functionally correct or related to properties like throughput or availability. And these are observable in the running system. We know a lot about how to test these. Early in the life cycle, we can build models and simulations, and eventually we can test the implemented system. The second category is qualities like observability, evolvability, composability, and integrability. These are important for systems that use MOSA, the Modular Open Systems approach. These are qualities that can't be directly observed in the running system, but we can see them in the development artifacts, for example, in the architecture views. And we can make measurements, we can apply analysis methods, and we can make judgments about whether these requirements are satisfied. Now, two comments about these categories. The first category isn't necessarily more precise or accurate just because we can see it in the running system. And it doesn't necessarily produce higher confidence results because we can observe it. The results in this category depend on factors like the fidelity of the models. And early in the life cycle, that fidelity could be low. And in the second category, we find that we can produce valuable judgments even using very early artifacts. And often our confidence in a negative judgment that the requirement is not likely to be satisfied can be pretty high. Over time, organizations that have instrumented their development process and collected data can make even higher confidence predictions about these qualities. So both cases, the results depend on the inputs and the evaluation process that you're using. Now, the other comment is the state of the practice for the second category is that the results today depend more on the skills and knowledge of the analyst that's doing the evaluation. And so that's what led the sponsor of this work, the Army Futures Command, Aviation and Missile Center Aircraft Development Directorate, to task the SEI to address this challenge. And the challenge is, how can we make this evaluation more systematic and repeatable for qualities like integrability and make it less dependent on the skills and knowledge of the analyst? And so our solution was to create a playbook for analysis for each of these quality attributes. And the process can be applied early in the life cycle, and can also be applied later in the life cycle, but our focus has been early evaluation. It provides practical guidance about how to specify quality requirements, about design mechanisms, the patterns, tactics, frameworks that typically appear in an architecture to promote the particular quality. We talk about measurements of the design artifacts and checklists and questionnaires that support the analysis and the judgment. And the outcome is that acquirers can verify that the architecture that they're getting will allow them and in their system to satisfy the goals and requirements that they have. Now, the process is divided into 3 phases and 7 steps. They're summarized here, and in the next slides, I'll go through them in more detail. As I mentioned earlier, our confidence in the evaluation depends on the quality of the input artifacts. Early in the life cycle, we often accept lower quality confidence results from artifacts that may be incomplete or less precise. Later in the life cycle, we can make higher confidence judgments, perform deeper analysis, and get more precise analysis from the completed artifacts. Now, the playbook process begins with the preparation phase. Here we need to decide if the quality of the artifacts will support the needed degree of confidence in the analysis results. The first artifact that we need to look at is a specification of the requirement to validate. And the playbook includes a general scenario that provides a template to specify a measurable requirement for the quality. And we also need other requirements. Remember, architectures make trade-offs, and we need to look at the big picture. And finally, we need some documentation about the architecture. Now, this need not be complete and release documents. Early on, photos of sketches from a whiteboard might be enough to get started, or a list of approaches that are being taken in the architecture. And later on, as complete architecture views become available, we can use those. And the next phase is orientation. The analyst needs to orient herself. This may be the first time that she's seeing the architecture. So we start in step 2 and first identify how does the architecture claim to address the requirement that we're evaluating. So let's take an example. We have a requirement about integrating a new sensor into a signal processing function. The rationale in the architecture documentation might say something like, well, this architecture uses a pipe and filter pattern, and that allows us to easily replace the sensor data ingest and integrate a new sensor. So now we know the approach that we're taking. We have some idea about the mechanism. In step 3, the analyst needs to find out where does this mechanism live in the architecture. In this case, the pipe and filter that was referred to, where is it and how is it being used? And we'll start collecting some data about it. If it's a pipeline like this, how many stages are in the pipeline? Sensor data ingest is the key to meeting this requirement. Is that actually a separable and replaceable stage of the pipeline? How do the other stages depend on it? And look at the overall pipeline. The analyst considers questions like, is the number of stages in the pipeline fixed or can it vary? And so the playbook has checklists and questionnaires that guide the analyst through probing into the use of the mechanism. Now, finally, in step 4, we're going to look more deeply into the mechanism as it's used in this particular architecture. So we have derived decisions. If the pipeline can vary, when does that happen? Is it built into the code, or is there runtime use of a configuration file? And most mechanisms have some special cases that you need to consider. For example, in a pipeline, if it can change during execution, what happens to the data that's being processed? So the analyst comes out of this phase with a good understanding of the approach that the architecture is using to satisfy the requirement. Now, this brings us to the evaluation phase. This is the meat of the playbook. In step 5, the analyst has to decide if the architecture approach is sufficient. Is the mechanism, the decisions, the derived decisions, and the special cases altogether going to satisfy the requirement? And again, here the playbook supporting material provides some guidance into making this judgment. Now in step 6, we're going to look at trade-offs. Remember, we collected other requirements in step 1. We need to look at them now and decide if we are breaking anything else as we instantiate this particular approach. So for example, the pipe and filter approach that we've been talking about in this example, it may help us in adding a new sensor or integrating a new sensor, but pipes and filters increase latency, right? And so the derived decision to use a configuration file may impact our testability because now we have test cases for different configurations. And so the analyst needs to ensure that nothing got broken with the approach that was used to satisfy the requirement that we're looking at. And the last step in the playbook is step 7, where we look at the cost benefit of the approach, right? In step 5, we've judged the sufficiency. Now we've got to look at the necessity. Every architecture mechanism makes the solution more complicated. It adds more components. This is unavoidable. If we want to solve real world problems, we need to add some complication to the solution. But some approaches also increase complexity. They add new types of components. In this example, we started off with a signal processing pipeline. Maybe we add a configuration file. This is a new type of component, increasing the complexity of the solution. And the analyst needs to decide if the benefit that's provided by the approach justifies the added complexity that it introduces. Now, this is a bit of a judgment call. But we think even when it's not 100% clear, it's worth asking this question. Is the approach necessary or is it overkill? So this is a short introduction to our work. You can find all the details in the SEI Digital Library, which provides free downloads and no registration required. We've released the playbook for the quality of integrability, and we have playbooks for maintainability and robustness coming soon. So thank you for watching this presentation. For more information, you can contact me at jklein@sei.cmu.edu or at info.sei.cmu.edu. Thank you.